I make it exactly 6 o'clock here in Tanzania, and so it will be 1500 hours UTC, and I suspect that's sometime in the morning in Washington and New York. Is that right?
11 o'clock. It's 11 o'clock.
11 o'clock, is it? Right, very good.
Mm-hmm.
Okay, and so I'd like to welcome you to the International Biometric Society Journal Club, which we try to hold on in the middle Thursday in the month, either the second or the third Thursday in the month, every other month. Hopefully you've accessed the webinar, which is through the ComPartners link, which was available to you when you registered, and you've also been able to log in to or dial in to the audio, which is through one of these toll-free numbers. And of course, if you are using Skype, then the best way to do it is to dial into the US toll-free number, and that will be absolutely free as well. Okay, so for the Journal Club, we have a few ground rules because we want to keep this open to all members of the Biometric Society so that they can understand it. So we'd like to make sure we keep it simple, and I think the presentations usually make the paper very easy to understand, so that's nice. We like to make it short. We will be limited to exactly 1 hour, so make your comments concise and to the point. Speak slowly and clearly because the internet may not be as good in some countries as others, and many people who are in IBS may not have native English to their advantage. Let's try and be constructive, build a discussion in a positive way. Let's make some nice points about how we can use the information we get. Respect others. Raise your hand if you want to speak, or just give me a little text in the chat box and I'll see that, and then I'll let you speak and ask your question. When you're not talking, if you can mute your microphone so that we can't hear all of the other background noises, and then we can concentrate on what's being said. All of the papers are available through the links in the left-hand side, and the recording will be made of this particular Journal Club as well. So at the moment, I would like to give my welcome and to the speaker today, which is Dr. Jennifer Pohl, and she will be presenting on. Sorry, go back to the beginning. Go back to the beginning. She'll be presenting on selecting the number of states in hidden Markov models. And so with no further ado, I shall hand it over to Jennifer to take us through a presentation of her paper. Jennifer.
Yeah, hello everybody. Thank you very much for the kind introduction, and especially thank you very much for the opportunity to present our work here today. I'm going to talk about our paper, Selecting the Number of States in Hidden Markov Models, Pragmatic Solutions Illustrated Using Animal Movement, which I was working on together with my co-author, Roland Langrock, who is also my PhD supervisor and present here today, and Floris van Beest and Niels Martin Schmidt from the Aarhus University. I'd like to start with our motivating example, muskox movement in Greenland, and this figure shows the movement track of our muskox Carla, which was tagged for about 34 months, so almost 3 years, using a GPS collar. Hence, the dataset contains 25,010 hourly observations of Carla's location, and to model the movement, we use the hourly step length and turning angles. There are two important features worth emphasizing. First, the movement of the animal is influenced by its behavioral mode. The shown graphic here displays a sequence of the observed step length, and we can see that there are periods of almost no movement, which could belong to a resting behavior, but there are also very long hourly step lengths, which could then belong to travel behavior. However, we cannot directly observe these behavioral modes. And second, the behavior seems to be persistent over time. We see in the graphic that there are periods of short steps followed by a sequence of long steps, for example. And these two features motivate us to model the movement using hidden Markov models. Let me just say at this point why we want to model the movement. Usually the aim of this study is to relate the behavior to internal and external drivers. This figure shows the basic structure of the hidden Markov model, or short HMM, and it is assumed that the observations are driven by an underlying non-observed state sequence. This sequence is assumed to be a Markov chain, discrete in time and with capital N states. And at each time, the current state determines the distributional form of the observation. So we get capital N state-dependent distributions for the observations. And furthermore, given the states, the observations are assumed to be conditionally independent of each other. Note here that these are, of course, very strong assumptions. They are made because they make our life easy and are reasonably realistic. But however, as we will see later on, these assumptions can affect model selection. And in the context of animal movement, HMMs are quite useful because the unobserved states can intuitively be interpreted as proxies for the behavioral mode of the animal which drives the movement patterns. Thus, the states are of great interest here. And now, to fit the model to the data, we need to estimate the initial and transition probabilities of the Markov chain, as well as the parameters for the state-dependent distributions. And this can be done using maximum likelihood estimation. And luckily, the likelihood can be written as a matrix product, and this corresponds to recursive calculation of the likelihood. Starting at the first time point, we traverse along the time series, updating the likelihoods as we go, but also maintaining information on the state probabilities. And the computational cost of calculating the likelihoods is only linear in t. And this is actually quite remarkable because what we're effectively doing here is to consider all possible state sequences that might have given rise to the observations. So having this recursive calculation of the likelihood, we can now use maximum likelihood estimation using standard numerical optimization procedures. And as a short remark, it is also possible to use the EM algorithm for maximum likelihood estimation. Oh, there's a mistake, maybe. Oh, there is a part missing on the slides. Yeah. However, so when we use maximum likelihood estimation, it is conceptually straightforward now to use information criteria to select the number of states. The most prominent are AIC and BIC, and these criteria are also often used in empirical works or studies. However, it has been shown, in particular in ecology, that these criteria tend to select more states than seem reasonable. And I would like to go back to the muskox movement now, and I wanted to provide a table of AIC and BIC values, but you can't see it on the slides. I'm sorry for that. So what we did is that we fitted HMMs with up to 5 states to our muskox data using gamma distributions for the step length and von Mises distributions for the turning angles. And what you could see on the table, if it was there, is that AIC and BIC select the most complex model with 5 states. And note that if we would continue to increase the number of states, both would actually select even models having at least 9 states. And those models are not interpretable anymore. And to see if the 5-state model is a reasonable choice, let's have a look at these fitted models. Okay, so here you see at the graphic the state-dependent distributions of the 2-state HMM, which was estimated, and these distributions are weighted by the stationary distribution. And on the left side, you see the estimated gamma distributions for the step length for each state, respectively. And on the right side, the corresponding von Mises distributions. It is very easy to this model is very easy to interpret. The green state captures short step length and undirected movement, hence can be seen as an inactive state, while the orange state captures longer step length and directed movement, and thus can be seen as the active state. For the three-state model, we see that the inactive state actually splits up, and we have now two states capturing shorter step length and undirected movement. This model is still easy to interpret. We could imagine the green state as a resting state, the orange state as a traveling state, and the pink state as a foraging state. Now let's go to the four-state model. We see here that in the four-state model, the active state splits up as well, and what we called, or I called, traveling mode before, now splits up into a state capturing a rather short distance traveling and a state capturing rather long distances. And this split up might still be reasonable, but it's difficult to say without discussing the biology. However, when we now have a look at the five-state model, we see that we get two states that are almost similar, the pink state and the green state here in the graphics. And both capture resting behavior, so short step length and undirected movement. And for us, this does not seem to be reasonable anymore, and it could simply be an artifact of temporal varying GPS measurement errors, actually. So the question arises, why do AIC and BIC prefer the most complex models? Our data set is actually very complex and contains many structures and dependencies. And note that the muskox lives in Greenland in a rather extreme environment. So the HMM, with its quite strong dependent assumptions, is not able to reflect all characteristics of the data set. It is rather a model of convenience here to model the behavioral modes in a feasible way. So what happens is that the additional states can absorb, or figuratively speaking, mop up the structure in the data that we neglect in the model formulation. And consequently, the states cannot be seen as proxies for the genuine behavioral modes anymore. I would like to demonstrate this point using a simple simulation scenario. What we did is we simulated 5,000 random values using a two-state HMM. And for the first state, we chose a simple gamma distribution. The second state, however, corresponds to a non-parametric distribution, which reminds on a gamma distribution, but possesses a heavy tail. And after the data generation, we fitted gamma HMMs with up to 5 states to the data. Hence, we fitted models that were slightly misspecified. And then we calculated the AIC and BIC values of each model to check which model they would select. We repeated this procedure 100 times. And the results of this rather artificial scenario are not surprising, but illustrate clearly the problems in selecting the number of states. So this graphics here show the resulting state-dependent distributions of the two-state model and the three-state model for one simulation run, so the estimated models. And we see that on the left side, the two-state model is not able to capture the complete distribution used to generate the data. However, in the three-state model, the third state, meaning here the pink state that you see in the graphic, is there to capture the heavy tail of the non-parametric distribution that we used. Hence, it compensates for the inflexibility of the used gamma distributions. And as expected, AIC and BIC chose models with at least 3 states in all our simulation runs. So this information criteria point to the models with, which exceed actually the number of genuine states. The important point here is that although this is a rather artificial example, it illustrates clearly that additional states can absorb structure that is neglected in the model formulation. We tried out more simulation scenarios which I cannot detail here, but they include outlying observations, individual heterogeneity, temporal variation in the transition probabilities, a semi-Markov and a higher order Markov chain as the state process, and the violation of conditional independence assumption. And the result is always the same. Almost any structure in the data that is neglected in the model formulation can be mopped up by additional states. Note that this is also true for the violation of the rather strong dependence assumption of the HMM. But why is this relevant for practice? You could argue that these structures should simply be incorporated in the model formulation. However, in reality, having complex data sets, we often face many violations of the model assumptions. And it would be computationally infeasible to incorporate all these into the model formulation. Furthermore, this could also distract from the actual study aim. And what are the consequences of this? When AIC and BIC point to a model with more than the genuine states, and we choose this model, we cannot interpret this model anymore. The states of this model do not correspond to the genuine behavioral modes. However, the additional states may improve the model fit and describe the data better. Therefore, when the aim would be just to predict the time series observations, having too many states may not cause any problems. And for example, for financial time series, this might not be very interesting. However, if you want to learn something about the state process and the genuine states, AIC and BIC may point to the models that are not interpretable anymore, or in this way. And for example, imagine making a meaningful ecological inference based on, say, a 13-state HMM for muskox movement. This is just not going to be feasible. Oh, there is again something missing on the slides. I don't know why. I'm sorry again for that. Can you see something on the slides except the title?
No, just the title. Sorry about that.
Okay. Yeah, sorry, there was supposed to be text. So I just tell you about it. So we were thinking about alternatives to AIC and BIC to avoid this problem, and we considered cross-validation and the integrated completed likelihood criterion. So for cross-validation, we also have a focus on prediction as the AIC, and we will typically not lead, the cross-validation will typically not lead to fundamentally different choices than the AIC. Actually, for the linear case, it is even shown that both are asymptotically the same. Furthermore, cross-validation is computationally demanding and very time-consuming. The ICL was developed for cluster analysis and is a BIC-like approximation of the completed data likelihood, which also includes the not observed but estimated state sequence. The ICL puts a stronger focus on partitioning the data, which can but is not in general desirable. Anyway, its behavior, and above all in the context of HMMs, is still poorly understood. So actually, we don't believe that there is one general applicable formal procedure for selecting the number of states. And we are really grateful to be able to discuss this paper here today, because maybe some of you may have any further suggestions about this. but as we didn't found a solution or one or a generally applicable formal procedure, we suggest the following approach. We are suggesting a more pragmatic step-by-step solution to select the number of states in the case that the aim of the study is to learn something about the state process. First of all, we suggest to choose a reasonable set of candidate models a priori to the model fitting and taking into account expert knowledge. Second, after fitting our candidate models that we chose in step 1 to the data, closely inspect each of the fitted models. And this can be done by plotting the estimated state-dependent distributions and the most probable state sequence. Third, model checking methods should be used to reveal major lacks of fit, and for this, the inspection of the pseudo-residuals can be used. The fourth step, for the fourth step, we still recommend to use model selection criteria for guidance, as a big difference in AIC or BIC values might still indicate a big lack of fit. And after these 4 steps, we think that a model can be chosen based on all previous results, but also by taking into account expert knowledge and computational considerations. And in the case that there are more models which seem to be equally fine, we recommend to report each of these models. I would like to demonstrate this procedure using the muskox movement data, and after having talked to the data owner, we included HMMs with up to 5 states in our analysis. So let's go to step 2, the model inspection. As you've seen before already, a 2-state model may be too simple to capture all the behavior of the behavioral modes of the muskox data. And on the other hand, a 5-state model has 2 states that are almost the same. I repeat, the pink and the green one. And therefore, 5 states neither are useful for the study in our view. The third step is model checking, and I will concentrate here on the step length. The graphics show the QQ plots of the pseudo-residuals for the step length, and when we inspect the plot of the 2-state model, we see that it indicates a lack of fit in the lower and the upper tail, and hence the model does not seem to capture the marginal distribution of the data very well. The other models look okay. But the plots of the autocorrelation function reveal a lack of fit for all models. There are within-day variations in the data which are not captured by our model. Notice the peaks at lag 12 and lag 24. It is interesting to notice, however, that this pattern becomes less severe when increasing the number of states. And this might be an indication that the states capture some of this temporal pattern, actually. For step 4, we look again at the information criteria of the data. Now you see the table here as well. You see now that AIC and BIC would select the most complex models with 5 states. However, the ICL points to the 4-state model. Now, after step 1 to 4, we can now choose a model. Just to summarize, the 2-state model does not seem to fit to the margin distribution, and no model takes into account the dial variation in the data. Also, the AIC and BIC point to the most complex model, but the ICL to the 4-state model. But as I said before, the behavior of the ICL is still poorly understood, and we don't recommend its uncritical use. Now, when it comes to choosing a model, there are 2 options here now, and it depends on the aim of the study which of the 2 should be pursued. Usually, one would incorporate the dial variation into the model formulation and then starts again at step 1. However, in the case that the dire variation and the minor lack of fit in the state-dependent distributions do not interfere with the study aim, we would report the 3-state and the 4-state model. Now a short summary, a short conclusion. We've seen that almost any structure in the data that is neglected in the model formulation may be mopped up by additional states. And this phenomenon is a peculiarity of HMMs rather than a general problem in statistical model selection. We believe that there is no one-size-fits-all objective criterion for order selection in HMMs. And while lacking objectivity, a pragmatic step-by-step approach to order selection is, in our view, the best possible practical solution. And the corresponding analysis will be as scientific, if not more scientific, than any eligible objective choice. Thank you very much for your attention, and I'm happy to discuss with you now.
Thank you very much, Jennifer. That was a very interesting talk. I enjoyed reading the paper, and I enjoyed even more listening to your description and presentation on the paper. I think we did have a discussant for your paper, but he's unable to be here. He got the times wrong for the meeting. So Jaakko Navalainen has a few points that he wants to make, and I thought I'd make a few points as well. Jaakko, do you want to go first?
Yes. Thanks, Tim, and thanks, Jennifer. Excellent paper. Very nice talk. Something new to me. I had 2 questions, basically, or comments. You make a point in your discussion that there's a connection to clustering, and obviously the problem of selecting the right number of clusters is an issue there. Now, in clustering, when you characterize the clusters, you get as an output, you do typically some descriptive measures or things like this. Here, you would try to characterize the states via the emission distributions, and I was wondering, is that always easy to do? I mean, it's a crucial step in the selection of the correct number of states. So I wonder if you have some further comments on that.
I'm jumping in here. Here's Roland. I'm sitting here with Jenny. So we co-authored the paper together. I'm not sure if I understood the question correctly. I mean, yes, there are, of course, some parallels to cluster analysis. So, I mean, one experience that we've made with HMMs is that there's very often, when you compare the different distributions across the states, there's actually strong overlap, whereas in cluster analysis, very often, you try to have a very nice separation of the clusters. And that's also why we think that the IACL criterion should not uncritically apply for HMMs, whereas for cluster analysis, it's very often the right thing to do. But it's probably not answering your question, is it?
No, I was more generally wondering if the emission distributions are always easy to interpret for an expert, since it's involved in the selection of the number of states. Yeah, perhaps that's clear.
The initial distribution just says in which state we start at the beginning of the time series, right? I guess you mean the stationary distribution of the Markov chain.
The emission. The
initial distribution. I mean, in our terminology, it's just gives us the probability of starting in the different states at time 1 of the time series.
All right, maybe I misunderstood something there.
You probably mean the stationary distribution, because the stationary distribution gives us an indication of how much time is spent in the different states. And that tells us something, of course, about how relevant the different states are. Is that what you mean?
No, I don't think so. I mean the distributions of the angles and distribution of the step lengths in your examples.
You mean the state value distributions? Emission distributions, you said.
Emission, yes.
Sorry, we misunderstood. We thought that you said initial like starting distribution. Sorry.
Right.
Oh, bad. Okay, then we have to think again.
Okay. Mm-hmm. And Jaco, do you have another question, or is that?
Well, the second thing I was wondering is that you said that the BIC seems to point into too large number of states, underlying states. And I've seen the same feature in some other latent class models. My student has been working on latent class joint models in the survival and longitudinal process context. And I was wondering, do you think this is something which is shared by different latent class models, that BIC might not be the criteria to go for? Or is it by coincidence that it behaves in this way for hidden Markov models?
Actually, I think it's the same problems with, for example, latent class models, because they are quite similar to HMMs. And I believe that it's possible there as well that, for example, a higher number of classes can just absorb some structure in the data that may be neglected by the model formulation. So I think that we've got the same problem there as well. But I didn't try it out yet, but that's my feeling for it. Because
so it's like if you have too many latent classes, it might be a signal of your model not being sufficient yet in some respect.
Yes. I think you could use the same procedure for selecting the number of classes there as well as we proposed for the HMM, because it's not necessary that the BIC point model to too many classes, but if it's like an unreasonable number, or the classes seem not to be reasonable, I think we could have the same problem there. So if the classes do not make sense for an expert, for example, but the BIC says that that's the number of classes to go. I think it could be the same problem there as well.
Okay. I mean, even simple mixture modeling, if you just think of a Gaussian mixture, like what people use in cluster analysis, when you just use a Gaussian mixture because that's what you have most easily available in software packages, but actually your data, your clusters, are not such that within the cluster you have normal distributions, but you have whatever heavy tails, you have outliers or something like that, then you could easily select too many clusters, too many components in your mixture model, simply to capture those outliers which don't fit to the normal distribution. Pretty much exactly like what Jenny showed in her simulation study. Oh, and I think that sort of thing would apply to any latent class model, wouldn't it?
Yep. I mean, it does seem to me that the knowledge of what you're looking at, so of where the data coming from, what the data mean, and the distributions that might be important for that is important. That's the very first step that you mentioned. And I thought that's similar to so many other areas of statistics. You need to know and not just choose something off the shelf, but to know really what your data are showing in order to be able to analyze it properly.
Absolutely.
Okay. Yep. So I want to open it up to other members of the audience to discuss. And I know that Prem Naveen has a question there, so perhaps I can ask him if you'd like to give that question to you.
Yeah, thank you. I guess it's a very interesting paper, connecting a very tactical problem to a very difficult modeling approach, See, I was wondering in this Markov models, the transition probabilities are time homogeneous. Now, is that assumption can be right in this practical situation?
Yeah, we assume the transition probabilities to be the same over the time, but this can be easily relaxed using, for example, time as a covariate. Or just any covariate to explain this.
You see, because you take when a 2-state model to a 3-state model to 5-state model, the transition probabilities vary and they become smaller compared to a smaller state model. So when that goes in your simulation program, it is taken care of. Does it make any difference, or it works all right?
I couldn't understand you initially when the first sentence was started because quality was poor. But I mean, yes, if there is variation in the transition probabilities over time, basically we need to account for that if we don't want these things to happen. This problem of ending up with too many states. I mean, we saw this in the muskox example where we have dial variation, which simply means, I mean, these animals they don't travel at night, so they don't visit the traveling state at nighttime, and we need to incorporate that into the model. So we just need to have our transition probabilities as a time of day, as a function of time of day, sorry, and then that will automatically improve the fit of the model, and then also probably lead to smaller numbers of states. It's conceptually easy to do that, but that's just one model component, and if there are other violations of the assumptions that we're making, then we need to change the model formulation in various parts, and at some point it just becomes infeasible. But in principle, yes, sometimes we need to account for that, and in principle we can account for that.
No, that's okay.
But in general, is it more efficient for you to add more variables in or more structure into the variables that you're putting into the model, rather than to allow the model to add more states or to add more states to the model?
Okay. Thank you.
What do you mean by variables? Do you mean variables in like covariates, or do you mean like step lengths and turning angles and things that we actually model?
Both. Both. Changeable variables. Yeah.
Maybe. Okay. Thank you.
Well, it's a complex question in the sense that the short answer is it depends, right? In principle, it's easy to do any of this. It's easy to have more variables, so multivariate time series. It's easy to have covariates, and it's also easy to have 3, 4, 5, whatever number of states. It's just, especially in these ecological applications, for the actual users, for the people working with the animals, tagging them and everything, for them it's crucially important that the states can be interpreted, right? That they have a very clear interpretation. They don't have to correspond one-to-one to biological behaviors, but at least there has to be some crude approximation of the biological behavior of the animal. Otherwise, people can't really use these models. They can't make sense of them. So in that respect, I would say, rather than in the muskox example, for example, rather than going to 7 states just to have a better goodness of fit, I'd rather try to incorporate dial variation, or maybe even relax the condition independence assumption, or go to a semi-Markov state sequence, whatever it takes, just to avoid increasing the number of states beyond what the biologist would like to see. But that's the answer, very specific to what we know from the ecological community, because they really do care about the interpretation. So if you talk to financial people, they don't really talk about this. They don't care about the states. They just want to make prediction for the actual time series observations. And then they don't care if it's 13 states or 17 states, as long as they get the best possible predictions.
Yes, so that was a point made in the paper, that these hidden Markov models are used in many different settings, and the different settings may want different things to come out of the models, and so what you're going to be using for financial forecasting might not be the same as what you'd use for ecological reasons. Yeah.
There's even another example, right? So when you go to the machine learning literature, where HMs are also heavily used, but mostly for recognition tasks, right? Speech recognition, activity recognition, and so on. and then they train these models to data where they know these states, right? So that the number of states is known a priori. It doesn't need to be determined. They know how many possible activities there are, and then it's a supervised learning exercise where the number of states doesn't play any role. It's automatically given to you. So that's the third possible type of application of HMMs. You have the forecast, as in financial applications. You have supervised learning applications where you know exactly what the states are and what they are supposed to mean. And then you have these, you want to learn something about, for example, animal movement, where you don't really know how many states there are and so on. That's the kind of thing that we focus on mostly. This is what the paper is mostly about. Hence the subtitle with the animal movement.
Right. Okay. Can I ask again whether anyone in the audience would like to ask a question? There's quite a few people in the audience who might have something to say about application of these hidden Markov models and might have some observations there.
Sure. Hi, Roland. This is Phil Dixon.
Hi, Phil.
You've got a very nice example of something I think is a quite general phenomenon, that as we consider models that get increasingly complex, the traditional model selection statistics only evaluate the entire model, the point that you make very clearly. But I wonder, you distinguished when the goal was prediction, you might not care so much about having a excessively rich state space. And I wonder if that's really true. You may be saved by having 34,000 observations, but isn't there a trade-off? As you increase the number of states, you have diminishing amounts of information about the characteristics of each of those states.
So, of course, we'd rather not have like a 40-state model, because that just gives us a very heavily parameterized model, which would be unstable. But that sort of is taken care of by these model selection criteria, right? I mean, the model selection criteria wouldn't point to these overly complex models because they have the penalty term on the number of parameters.
But I think, for example, when you have, for example, a second-order Markov chain instead of a first-order Markov chain for the state process. And this could be taken care of, like having a bigger state space, actually. But then the states, like they describe well the data than the model with like many states, but the states do not correspond to any like genuine states then anymore. So that would be nice for prediction, but maybe not so nice for the interpretation.
Actually, I think there are all sorts of problems with that. I mean, even in the financial applications, when you start going into models with 10 or more states, there are all sorts of problems with that. First, I mean, just having a transition probability matrix with 100 parameters is probably not going to be a sensible thing to do. And I think what you're trying to say, Phil, is that even there, it's a bit of a problem if there's no actual meaning of these states anymore. Is that what you're trying to say?
Yeah, just you sort of separated out prediction as something where lots of states might not be too bad, and I wonder whether you might actually run into the same sorts of issues with diminishing quality of predictions that are for out of sample predictions that are masked by and not detected by AIC or BIC.
Yeah. So it's probably better than to try to capture the actual structure rather than doing this mopping up thing, where rather than really looking into what is the structure and trying to build the model accordingly, we just do like Jenny just said. We extend the state space more and more until eventually we've captured most of it. I can see why this may not be a good thing at all to do also in prediction tasks. But at least in that case, if you do want to do prediction for the actual time series, say in financial time series modeling, and the AIC points to a model with 13 states, then you should probably go for a rather complex model, instead of trying to somehow justify with our pragmatic order selection why you would use a three-state model. It's probably there is some reason why we need that many states, and that could be, of course, dependent structure, which we may also otherwise capture. But at least in that case, there could be a justification for using that many states.
Thank you.
Thank you. Okay, so I think John Hind has a question that next.
Thanks, Ed. Yeah, so you were talking about mixture models, and one possibility in mixtures is to have a sort of component with very large variance to soak up all sorts of noise so that you don't sort of get contamination of some underlying structure in some other clusters. Now, is there any sense in which a similar idea can be done here so that you essentially switch between the true process, which has a small number of states that reflects the animal behavior, and some sort of noisy, very noisy state where you're getting contamination of your data?
Yeah, sorry, we were starting to discuss it here now, Jenny and I. I mean, in principle, yes. For some things, yes. I mean, if you're thinking of, just to give a concrete example in movement modeling, if we have extreme outliers, and there's no way of getting rid of these outliers, say by smoothing the animal track or something, yeah, sure, we could have such a rubbish bin state, or whatever you want to call it, where we just try to throw in all these observations that we can't otherwise explain. So how do you do this in mixture modeling? If you have this state which is not actually interesting, which just takes care of everything you can't otherwise model, do you fix that state a priori? I mean, the component distribution of that mixture component, or do you also estimate that from the data?
So I mean, some of the applications fix this with a state with a very large variance.
And so it's just chosen in some ad hoc way. You just look at the data and say, all right, I'll just take it.
Yeah, in fairly ad hoc ways. Of course, it doesn't get over the problem if you've got sort of misspecification of distributions. Then your extra states are going to try and pick up, model that extra structure that you haven't got there. And the same would happen in mixtures as well.
I mean, I can see this potentially working for this simulation scenario that Jenny outlined, where the emission distribution is the problem, but that's just one of many possible problems, right? So in the muskox example with the 5 states, we had these 2 resting states, which we think just correspond to measurement error of type 1 and measurement error of type 2, respectively. So sometimes the muskox will simply be in an environment where the measurement error is maybe up to 3 meters, and then other times it's up to 8 meters, and then we get 2 states for this, which we don't want. But we couldn't get rid of this by just having this extra artificial state with a high variance. So this is just one example where I think it wouldn't help. On the other hand, I can see why in other scenarios where we have outlying observations, extreme observations, it could work, it could help. But all these things are very problem-specific, right? I think this just confirms once more that it's really hard. It's going to be really hard to come up with a criterion which people can just use in any scenario where they use HMMs and not think too much about them. I think Jim said it earlier. It's one of these things when you work with real data here, HMMs fitting to real data, you really have to think hard about the study aim, the data at hand, you have to talk to the users and so on. It's not going to be possible, I think, to have the criterion which will work in almost every HMM application. And this is, I think, sort of the main message of the paper, because people are always looking for these criteria, especially the ecologists now who apply HMMs all over the place. They want answers. They want, can I now use the BIC whenever I do this, or can I use AIC? And the answer is simply no. You have to think instead.
And also, like the idea of your second step of looking at the residuals, which is really what you're doing there, to see whether there's any patterns that need to be further investigated before you do any criterion evaluation.
Yeah, that's also very often overlooked, right? Especially in the more applied communities, and you get these fancy tools like HMMs, and you apply them, and then people are very often satisfied when it's a bit negative the way I say it here, but I think you know what I mean. I'm slightly exaggerating here, but when people get the tool like an HMM and you give that to an ecologist or also to somebody in medicine or someone, then people are very excited if they get it to work, and then they don't apply the statistical rigor that we would like them to apply, which in particular means very thorough model checking. So in all these papers on analyzing animal movement, you hardly ever see any model checking, which is of course a shame. But it's hard. It's not like regression analysis. I mean, even calculating the residuals for HMMs is not a trivial task to do.
Sorry. Okay. Any other questions from the audience? Anyone else want to have a chance to ask another question? I think that's been a very interesting and informative talk, and I'd like to thank Jennifer and Roland for their inputs into the Journal Club. Hopefully, I'd like to also thank the IBS Secretariat who have put this on and made it work. I mean, it's been a little bit short-handed for them because they were they've been changed in the IBS Secretariat. But thank you for them as well, and thank you for Jennifer and Roland and for the paper, which I found very interesting. I knew nothing about hidden Markov models before this, and I've learned quite a lot from the paper and from the presentation. Thank you again. We'll have more information on the next Journal Club very soon, and we will have a meeting in December, and we'll keep that there. So anyone want to say anything in the final few minutes that we have, just to say how much they enjoyed this or anything about what we can do to move this forward? Any final comments? If not, I shall say thank you very much, and welcome again next month, and hopefully we'll have another paper which is just as interesting and some discussion about that in December. Thank you very much.
Yes. Thank you very much as well.
Thank you, Jennifer. And thank you, Roland.
Yeah, thanks for having us. It was great fun.
Yeah, good. And thanks to the audience as well. Okay.
Thank you, Dr. Todd.
Thank you. Bye-bye.